Thank you very much, Enrico, for the kind introduction. And also thank you to all the organizers for inviting me to give in these lectures. It's a pleasure to be here. I'm just sorry we cannot be in person in the same room, but it is great to be here nonetheless. So my task is to give you an introduction to effective field theory methods. And from this viewpoint, I would say that these lectures stand apart from other lectures that you'll be seeing in attending in the school, since other lectures are, if you want, you know, centered around aspects of nature that we either already see or we hope to see in the near future, like physics beyond the standard model, for instance. Whereas effective field theories instead are a tool. And so if you allow me a slightly cheesy analogy, while in other lectures you will learn how to play music by all the most famous composers like Beethoven and Mozart and so on, in these lectures instead you will learn how to build your own violin if you want. So without further ado, let me just share with you the plan for these lectures. And I'm having a problem here. I don't seem to be able to share my iPad screen. I don't know what's going on.
Yeah, so we're yes, we're seeing the general Zoom page. Yeah, I don't know.
Let me check. It says that my sharing is paused. Oh, how about now?
Okay.
Okay.
Now we see it.
Excellent, excellent.
Okay, good.
Okay, very good. So, as I was saying, let me start with the lecture plan. And these lectures will mainly consist in 4 parts. The first one, which is also going to be by far the shortest one, I'm just going to give you a brief overview of the basic ingredients of any effective field theory. Okay. So in this section, I'm not going to take a historical approach that will start probably from the renormalization group and build on that. Instead, I will briefly just summarize what is our current understanding of effective field theories. And then in the remaining 3 sections, I will try to introduce the main ideas, concepts, and techniques in effective field theories, starting from some concrete examples. And the first example that I will consider, the second part, is just going to be a toy effective field theory with a scalar field and a fermion. This field theory has no pretense of describing anything in the real world, but as we will see, has already enough interesting features that will get us started with our discussion. In the third part, I will discuss a class of effective theories that actually are closer to what we see in nature, although not quite at the LHC, but and these are effective field theories for Nambu-Goldstone bosons. So as you might know, Nambu-Goldstone fields appear anytime some symmetries are spontaneously broken. And the way in which the symmetries are implemented on these fields is can be very complicated. It's a nonlinear way. And so this presents additional subtleties when it comes to writing down effective field theories for this type of particles or fields. And in the last part, we will talk about effective theories for non-relativistic fermions. And the 2 examples, concrete examples that I will give in this last part are going to be one is going to be relevant for particle physics, of course, since this is a particle physics course. And another one will actually be relevant in condensed matter. And I guess it seems appropriate since these lectures are titled Effective Field Theories for Particle Physics and Beyond. And part of that motivation for that is to try to convey the idea that effective field theories are really a general language that we can use to describe any phenomenon in nature, not just in particle physics. Okay, so before diving right in, just a few quick notes. As you will notice, I will start from something very basic, and then we will work our way up to more technical details. There might be some possible overlap with some of the contents you see in other lectures, although I hope that more than just being a repetition, this is actually going to just provide a different viewpoint on certain topics if you want. I might, if time requires it, I might omit some of the details compared to the notes that are posted on the website, but I will do so only when these details are not crucial for what we're discussing in class. And similarly, I will not mention explicitly the exercises that are embedded in the lecture notes. This is not because the exercises are not important, quite the opposite. So I actually encourage you to try your hand and try to solve some of these exercises. There are probably more exercises than the time you will have to work on them, but at least try to work on a few of them. All right, so oh, and the last thing is that I'm not keeping track of what's going on the chat, so I will rely on Enrico in case there are some pressing urgent questions that come up there to just stop me and so that we can address them. All right, so let me start with the first part of these lectures, basic ingredients of EFTs. And I would like to start with a very general observation, which is that there is an amazing fact about nature that we often take for granted, which is that there is a remarkable array of interesting physical phenomena that take place over a very wide range of scales in nature. Okay? So we could talk about length scales, energy scales, time scales, you pick. But let me, for the moment, just stick with length scales and sort of arrange them in a logarithmic scale. Then to the okay, so I guess in here they're supposed to be at 10 to the 15. And everywhere on this scale, everywhere we've probed, we can find very interesting physical phenomena, starting from nuclei and subatomic particles all the way to the left of the spectrum, and to the whole observable universe, its accelerated expansion, its dark matter content, and so on, to the right of the spectrum. And in your departments, you might have colleagues that work in this regime, atomic physics, biophysics, worried about cells, astrophysicists that look for exoplanets and care about physics going on at this scales, and so on and so forth. Okay. And the fact that all of these phenomena happen at different length scales, different energy scales, different time scales, it's actually a blessing for physicists, because had all these phenomena occurred roughly at the same length scale, most likely we would have had to understand them all at once in order to make progress in physics. And that would have been just an incredibly hard task. Instead, because all these phenomena are spread out over different scales, there is actually a basic trick that we use over and over again in physics. And that is that if you're interested in a phenomenon that takes place, say, at some energy scale E, then you can, in a first approximation, take all the scales that are larger than that characteristic energy and send it to infinity. And all those that are smaller, send them to 0. And then, if you want, so by doing this procedure, the physics that takes place at these other scales decouple from this physics that you want to study. And but its effect can always be reintroduced, if wanted, in perturbation theory. Okay. Now, whether or not we admit it to ourselves, this is implicitly what every physicist does when they decide to focus on a certain phenomenon and neglect everything else, right? So, for instance, when condensed matter physicists study a certain material without worrying about the fact that the universe is expanding at the same time, they can do that precisely because the scale that is typical, the characteristic scale of the expansion of the universe is really, really, really different than the scale that are typical for condensed matter systems, and so on. Okay. And so this procedure of decoupling can be implemented by relying on hierarchies in length scales, as I said, or energies, as we more often do in particle physics. But you can also rely on hierarchies between masses or velocities, say, compared to the speed of light, and so on and so forth. Pretty much any dimensionful quantity will do from this viewpoint. Okay? And when you look at physics and physical theories this way, we find that pretty much any theory, when properly formulated, should actually be an effective theory. Okay, because effective field theory are precisely a framework that makes this cartoon picture that I gave you of sending large scales to infinity and small scales to 0, makes this picture quantitative and very precise, and we'll see as we will see in these lectures. Okay, so effective field theories are described by an effective action, okay, or its integrand, an effective Lagrangian, and you can build an effective field theory essentially by specifying 3 ingredients. So the principles are very easy to state, as you will see. It's the implementation that can often be complicated. So the first ingredient that you need to specify to define an effective field theory are its degrees of freedom. Sometimes these degrees of freedom will be forced upon you by symmetries, as is the case in spontaneous breaking, where Goldstone's theorem tells us that we are bound to have some Goldstone modes in our spectrum. But more often than not, the degrees of freedom of a system are just an independent input. Okay. Sometimes it's easy to figure out what are the degrees of freedom of a system. Sometimes, especially when the system is strongly coupled, it can be much more complicated. The second input is that you need to give are the symmetries that constrain the dynamics, or if you want, the form of your effective action. And now symmetries can come in a variety of ways, right? They can be global, they can be gauge symmetries. Some of them might just be approximate. We said they can be spontaneously broken. Some of them might be broken by quantum effects, which might be anomalous, and so on and so forth. And we'll encounter all of these in due time. Right? But for now, let me just say that once you have identified your degrees of freedom and your symmetries, one of the main tenets of the effective field theory ideology is that the effective action should contain any possible term that is compatible with the symmetries and is built out of your degrees of freedom. And as a result, in general, the effective action will contain an infinite number of terms. Now, in order to deal with an effective number of terms, we need also a third ingredient, which is an expansion parameter. This is the third defining property of any effective theory. And it could be a ratio of energy scales, E over lambda. It could be a ratio of velocities over the speed of light, for instance, or other characteristic speeds, and so on and so forth. Okay. What these expansion parameters do, they capture perturbatively the impact that the physics we have neglected can have on the physics we've kept and we're interested in. And in order for the whole program to make sense, the whole effective theory program to make sense, one needs to be able to assign to each term in the action a definite scaling in these expansion parameters. Okay. So, and this is what goes under the name of power counting. So then the name of the game in effective field theories is trying to implement correctly these three ingredients. Okay, you need to, for a given system, figure out what are the relevant degrees of freedom, what are the symmetries of the system, and what are your expansion parameters. And if you can do that, you have an effective theory. Now, these are very easy to state, but as many lofty principles in life, oftentimes they're easy to state, but difficult to live by. And so what we will learn in these lectures is we'll figure out how to implement these three principles in various different examples. We'll discuss what kind of difficulties you might encounter and possible ways of overcoming them. Okay, so this was sort of a bird's view of the principles behind effective theories. It's okay if some of the remarks I made at this point are not entirely clear, because hopefully they will become clear once you have seen a few examples. All right, so maybe this is a good time to ask if there are any preliminary questions before we dive right in and start discussing our toy effective field theories.
So there was a first question, Riccardo, asking whether you're going to discuss Silch and Borsov basis in the standard model effective field theory.
No. So what I will try to do in these lectures is to discuss the main tools in the of effective field theories in the simplest possible context that I could think of. Okay. So my hope is that by the end of these lectures, you will have all the tools, or at least most of the tools you need, to then go and look at the particular effective theory or a particular system you're interested in and study it using effective field theory methods. So my hope is that, yeah, although I won't be discussing that in particular, that by the end of the lectures, it should, if you read about them, you should, you should be able to understand what's going on.
Are there more questions for Riccardo at this moment? What are the pros and cons of EFTs?
Okay, okay, this is a good question. So I have a section about it in my notes, which I was going to gloss over just because I was afraid that some of these comments would be a little vague at this point. But let me just highlight a few advantages. That's a very good question. So why should we bother in the first place, right? Now, clearly, one advantage is that by focusing directly on the degrees of freedom that are relevant for a phenomenon, you are simplifying your life from the get-go. Okay. So, right, condensed matter physicists don't need to worry about quarks because at those scales they don't play any role, right? And the right degrees of freedom to use there are, for instance, protons or nuclei and electrons or even atoms. Okay, so trying to focus on the correct degrees of freedom, the relevant degrees of freedom from the get-go can really simplify your life. And that's often something we do already sort of without even thinking about it, right, intuitively. Now, when in more complicated cases, for instance, in strongly coupled systems, as we will discuss, when you do that, you might also uncover some symmetries that otherwise would have been hidden. And as we know, when you have a symmetry, there are oftentimes general considerations that you can make and general results you can derive usually with little calculation just on symmetry principles. So that's another advantage. One advantage in particular that we will discuss hopefully today is that it's a little more technical when you calculate loop diagrams in a field theory. If your field theory has many different scales, you might encounter logarithms of the ratios of the scales. And if these scales are widely separated, these logarithms might become large and might worsen the accuracy of any perturbative calculation you do. So effective field theories provide you a recipe to actually deal with these large logarithms by splitting the scales and treating them one at a time. Okay, so that's if you want a more computational advantage of effective field theories. And the last one I will mention is that since one of the main ingredients of EFTs are these expansion parameters, by keeping only certain terms in the action and dropping the ones that scale with high powers of the expansion parameters, you are already you can already have an estimate of the accuracy of your calculation. Okay. So this is something that I'll actually go much more into detail later on. But the fact that EFTs have built in this mechanism, not only they can make you predictions, but also give you an uncertainty on that prediction. It's also another advantage of this way of looking at it. And there are others that we'll encounter in due time.
Okay, there is another question. I don't know. Do you prefer to continue and then we get back to the questions later on?
Well, maybe why don't you read the question and then
yes,
depending on what's the question, we might go on or.
Okay, so let me read it to you. So can you please give an example where the degrees of freedom of a system is independent of anything? It's independent of our choice. It is our choice.
It is our choice.
Yes.
Well, so let's say, okay, it is not really our choice. Ultimately, it's nature that decides, right? But nature seems to have decided at the scale, say, relevant for condensed matters to have protons, neutrons, and or for nuclear physics, I should say, protons, neutrons, and electrons. And as far as we know, we don't understand why that is the case. It's an independent input. Someone had to discover at some point the electron in an experiment, the proton, the neutron, and given those experiments, we realized that a field theory that describes what's going on at those scales needs to involve these degrees of freedom. Okay? But I was trying to contrast, I would like to contrast that with, say, a situation like when you have spontaneous symmetry breaking, where just symmetry considerations tell you that at low energies, you must have a certain spectrum of massless particles. You can always add more particles, and that's where your choice comes in if you want. But those particles must be there, and they're forced on you by symmetry. Okay. Okay, I hope that answers the question.
Yeah, so there was another question, but it has been already answered in the chat. I think we can move on, Riccardo.
Okay, then let me move on. And let me define the toy EFT that I would like to use for the rest of this lecture, and also for part of the next one. Okay, as I said previously, it's going to be a theory that involves a single scalar field and a single fermion field. And it's going to be defined by this Lagrange. So I'm going to call capital M the mass of the scalar. I'm going to call little m the mass of the fermion. Okay? And so this is going to be, for those of you that know the difference, a Dirac spinor, just for concreteness. Okay? And then I will have Yukawa type action between the spinor and the scalar with a factor of gamma 5 there, and a quartic self-interaction for the scalar. All right. So this is the action we'll be playing with today. A few comments about it. In terms of symmetries, notice that because of this gamma 5 here, psi bar gamma 5 psi is a pseudoscalar, so it's odd under parity. And therefore, this whole action is invariant under parity only if phi is also a pseudoscalar, which means goes to minus phi under a parity operation. And this is the reason why there is no phi cube term. Okay? Phi cube term, this action would break parity. Now we'll be interested in working in perturbation theory. So we'll work in a regime where the couplings Y and the coupling lambda are both much smaller than 1. And at least for today, we'll focus also in the regime where the mass of the scalar is much larger than the mass of the fermion. And imagine now that we want to use this theory to describe, say, 2-to-2 scattering of fermions at energies that are much smaller than the mass of the scalar. Okay. Now, because our couplings are small, we can work in perturbation theory. And as you know, in perturbation theory, we can describe scattering using Feynman diagrams. And at lowest order, the scattering process is described by a Feynman diagram of this form, where the dashed line stands for the scalar. And let's say the scalar is scaling a momentum for momentum q. And to be precise, there is also going to be the similar diagram where 3 and 4 are interchanged. And the full line, of course, denote the fermions. So if you write down the corresponding expression for these diagrams, it looks like so. There is a Yukawa coupling squared I'm gonna drop the indices. You can find the correct indices in the notes, but just here I'm mostly interested in the overall structure. Okay, just looks something like so. Side remark about conventions, they're all spelled out in the notes. As you see, in these lectures, I will use a metric, which is mostly plus. Okay, that's why my propagator here has a plus. So if our fermions have energies that are much smaller than the mass of the scalar mediator, then generically also Q must be much more, the magnitude of Q must be much smaller than capital M. And this means that in a first approximation, I can write this amplitude also as U bar gamma 5 U, 1 over M squared, U bar gamma 5 U, okay? Plus higher order corrections that go like 1 over M squared times order Q squared over M squared. Very good. So now, in order to do that, all I need is for E to be much smaller than capital M. In fact, for the discussion that is going to come in a little moment, I'm also going to assume, just to make our life simpler, that the energy is also much larger than the mass of the fermions, so that the fermions are essentially relativistic. Yeah. Now, if we look at this amplitude here, at this order, we could have obtained this also from an effective action that only involves the fermions and has the following form: the standard kinetic term, and then a quartic self-interaction. Okay. So this should be nothing revolutionary for those of you that are familiar with the SAIFR theory of weak interactions. What essentially we do here, we've done here by taking this limit, we have found a description for this scattering amplitude that only depends on the fermion and doesn't include the scalar. And we have replaced these diagrams here with a scalar mediation with a single diagram with a contact interaction. Okay. Now, the fact that such a theory, such a description exists is makes a lot of sense intuitively, right? Because when you are at energies much smaller than the mass of the scalar, energy conservation prevents scalars from being created in scattering events. So if you were an experimenter that is confined to such low energies, you wouldn't have a way of discovering this heavy scalar. Okay, this was actually for the longest time the case when it came to weak interactions, say, until we saw the W and the Z. And so, yet, we know now by experience that an experiment that doesn't know about very heavy particles can still find a reasonable description of low energy scattering experiments. Okay, And so from this viewpoint, it makes sense that such a description exists. And in fact, I would like to argue that, in going from our full theory to the effective theory, I've dropped for now, we're going to come back to those terms that are suppressed by powers of E squared over M squared. But imagine that imagine that you are an experimentalist and that your experiment doesn't have, has a sensitivity, which is, imagine that E squared over M squared is much smaller than the sensitivity of your experiment, okay? So that effectively you can only probe this leading term in the amplitude. Then I would like to argue that, and let's say that you can also probe only 2-to-2 scattering, and that's it. That's the best that your experiment can achieve. Then I would like to argue that this effective theory is as good as the full theory. And in fact, it is better because by Occam's razor, it is a simpler description of exactly the same physics, at least as far as this hypothetical experiment can tell. And so it is in no way inferior to the full theory that we started with, until of course you go to high enough energies that you start seeing the scalar, and then you need to take that into account and you need to include it in a consistent way in your theory. Okay? So this is sort of a baby example of how an effective theory would arise at low energies from some hypothetical full theory, our toy model. And there is one important feature of this effective theory also that we shouldn't take for granted is the fact that it's a local theory. Okay, so it's an integral over d4x of some Lagrangian where all the points, where all the fields are evaluated at the same point. And an intuitive way of understanding why our action turns out to be local, our effective action turns out to be local, rather than involving products of fields at different points, is because exactly like the photon mediates a 1/r Coulomb interaction between particles, as you know, a massive particle mediates a Yukawa potential. So something, oh, sorry, 4 pi, something of this form with an exponential damping. So by focusing on the regime where the momentum exchange Q, which is of order E, is much smaller than the mass of the scalar, we're essentially probing this potential with a resolution delta R of order 1/Q, which is much smaller than 1/m. Okay. So this means that our resolution is much larger than the decay, the typical decay length of this potential. And in this regime, this potential, the exponentially drops off incredibly fast from this perspective, and essentially the potential reduces to a point-like interaction. Okay? And so only fermions at the same point essentially can interact with each other. This is a back of the envelope way of understanding where locality in this theory comes from. Okay. So what I've done here is so far is just a very simple example. I've only kept one term in the effective action, and I've only focused on 2-to-2 scattering. So I've only looked at the 4-point function. But you could, and at lowest order in E squared over M squared. But you could, of course, ask, can we extend this to higher order, to higher point functions? What about loop diagrams? And as I said at the beginning, the effective action, in principle, should contain an infinite number of terms. each of these terms should come with an arbitrary coefficient in front. Let's say these ONs are all the terms in the Lagrangian. The CNs are the coefficients, which are also known as Wilson coefficients. And you see an example of operators, for instance, could be this one. This would be one of these ONs. And this would be the value of the Wilson coefficient at tree level. So in general, your effective theory will have an infinite number of these Wilson coefficients. And if you want to go from the full theory to the effective theory and get the same physics, what you should do is figure out what are the correct values of these Wilson coefficients so that at low energies you get exactly the same physics. Okay. So in this example, this value here is what gave us the correct 2 to 2 amplitude at tree level at lowest order. In general, one would need to do this, one can do this also for other Wilson coefficients and working at loop order as well, and we'll see how to do that. In practical calculations, this procedure of figure out the values of this coefficient is known as matching. And in practical calculations, this is done by just comparing scattering amplitudes in the effective theory and in the full theory. But it is helpful to have a more a more general viewpoint on how matching works and what is the relation between the full theory and the effective theory. And so that's what I'm gonna show you now in a moment. Let me maybe pause and see if there are a few more quick questions.
So yes, there is a question asking if EFTs are scale dependent.
Yeah, so we will see later on when we match the full theory and the effective theory in this particular example, that the coefficients of the effective theory must be scale dependent, will depend on the renormalization scale. Yeah.
More questions? Okay, I think we're fine.
Okay, so let me go ahead now. So as you might know, in scattering experiments, we're interested in S matrix element, so the probability amplitude of going from some initial state to some final state. And the LSZ formula actually relates these matrix elements to time ordered expectation values of fields on the vacuum. Okay, I'm using phi here, but we could have psi's and any mu's, any fields you have in your theory. And in turn, this type of expectation values can be calculated systematically from a path integral perspective by introducing a generating function. Okay. So this is a quantity that depends on some external currents. And it's a path integral over all your fields. In our case, we have phi, psi, and psi bar. And you have the exponential of your theory plus I integral of j phi plus eta bar psi plus psi bar eta. And the idea is that by taking derivatives with respect to the currents, every time you take a derivative, you pull down a phi or a psi. And so you build a product of fields. And once you set all the currents to 0 after taking all the derivatives, what you're left with, if this generating function is appropriately normalized, is just the correlation function that you need to then calculate a scattering amplitude. Now, if you are at very low energies and you can only have access to the fermions, in practice, all you need are the correlation functions of fermions, which means that you can set to 0 from the beginning the current J. And when you do so, you can, the integral over the scalar only hits the part that depends on the action. So you can rewrite your path integral as e to the I integral of eta bar psi plus psi bar eta times the integral d phi of e to the I s phi and psi. Okay. And now, if you are strong enough that you can calculate this integral exactly, then this, by definition, is the effective action, which only depends on psi. Okay. And now this effective action defines a generating functional that gives you all possible correlation functions for the fermions. Okay. This procedure of eliminating the scalar is also known as integrating out the scalar, because we're performing the integral over the scalar. And in practice, we always perform this type of integrals in a perturbative way. And one perturbative scheme for calculating this integral is a loop expansion. So you can think of if you reintroduce all powers of h bar, turns out that this effective action admits an expansion in powers of h bar. So there is an S0, S1, S2, and so on. And where the zeroth part of the effective action describes all possible tree-level interactions. The one part describes all possible one-loop corrections, and so on. And what we consider above here when we wrote this effective action was just a subset of terms that live in so-called S0. So S0 is particularly easy to calculate, actually, because you can obtain it by performing a saddle point approximation of this full integral over phi. So that is to say that essentially you calculate this integral by evaluating phi by replacing phi with a solution to the equation of motion for psi. Okay. So when you take a solution of this equation, from this perspective, psi is some external field, you plug it back into the action. What you obtain is the effective action for psi. Okay, so to be precise, S0 effective of psi is S of phi hat psi, where phi hat satisfies this equation. Now, if you follow this procedure for starting from the full action that we have here, and you solve for phi in a perturbative expansion of derivatives suppressed by the big scale capital M, then what you find is an action that looks like the one we had before, plus an infinite number of terms. Okay. In particular, there are going to be terms that contain, say, things of the form psi bar gamma 5 psi, box to the n at psi bar gamma 5 psi, suppressed by some n to the 2n. There are going to be terms psi bar gamma 5 psi to some power m, suppressed by some proper number, power of m, and so on and so forth. Okay, you can find the first few terms in this expansion in equation 12 of the notes. And all these terms appear with some specific couplings that depend on the Yukawa coupling y and on the scale m and on lambda. So the particular values of these couplings are precisely such that the three-level predictions at low energies match between the effective theory and the full theory. Now, the reason why, in the case of our toy example, we can actually derive a perturbative expansion for our three-level effective action explicitly is because there are two reasons. One is that we know what the full toy theory is. We know that we're starting with this Lagrangian here, with this action. Okay. Now, in nature, it is not always the case that you know what the full theory is. Sometimes you're just stuck at low energies and you need to do the best you can. But the other reason is that the effective theory is also weakly coupled. So we can work in perturbation theory in powers of y and lambda. Okay. There are situations like in QCD where you may know the theory, it's QCD, but at low energies it is strongly coupled. And in that case, you might have to calculate the Wilson coefficients numerically rather than perturbatively in an analytic way. In other cases, like is the case for the standard model, we have ideas about what the physics beyond the standard model might be, but we don't know for sure. In that case, if you view the standard model as an effective theory, you should still add all possible interactions to the ones in the standard model. With some arbitrary coefficients, and those coefficients will essentially parameterize the effect of physics at high energy that you're not including. So EFTs cannot be used in this context to give you a general framework to constrain physics beyond the horizon of what you have already seen in experiments, essentially.
Riccardo, sorry, we have an urgent question, I guess.
Yes.
So they are asking why you have set j equal to 0 in the derivation when you are integrating over the scalar.
Thank you. Yes, I went a little fast on that. So, right. So this generating function depends on three currents in general. Because in general, for the full theory, you might be interested in calculating processes that involve both scalars and fermions, right? But if you are at low enough energies that you cannot produce any scalar in scattering experiments, then essentially the only correlation functions that you need to calculate are correlation functions that involve fermions. Right? And which means you will never need to take a derivative with respect to J to pull down powers of phi, and therefore might as well set j to 0 from the very beginning. Okay, and that's why I was focusing on this low energy regime. That's why I set j to 0 at the very beginning.
Okay. I think there are no. Okay. I think there are no other questions.
Okay. So okay, one more small comment. So far, I really emphasize the fact that you want to choose the Wilson coefficients, say in this case of the 3-level effective action, to match the 3-level amplitudes. So to really have the same physical predictions. But in practice, you are free to match the theory any way you want. You can calculate quantities that are unphysical, like scattering amplitude, say with zero vanishing, with vanishing external momenta. If that's easier, you can match those and then use the matched Wilson coefficients to calculate explicitly physical quantity. Okay. So I emphasize the fact that we want to, at the end, have the same physical prediction, but the way you get there, sometimes it might be more convenient to take shortcuts and compare things that are unphysical first. Okay, so now, as I said, when we integrate out the scalar field, we obtain in principle an effective action that, as advertised at the beginning, contains an infinite number of terms. Right? Now, when we start studying physics and we study Lagrangian mechanics, we never encounter infinite Lagrangians, right? Look at the harmonic oscillator, for instance. The hydrogen atom, the Hamiltonian of the hydrogen atom, they always contain a finite number of terms, right? And so, or even, you know, the standard model, we're often taught that we need to stick with renormalizable interactions. That's a finite number of terms, and we're all happy. So some of you, I certainly was as a student at the beginning, might be uncomfortable with the idea of having actions that contain an infinite number of terms, right? How do you deal with that? Is this predictive even? Having an infinite number of Wilson coefficients. And the key here is the fact that an EFT is defined with a notion of expansion parameter. So if in effective theories, there are only a finite number of terms that contribute up to a given order in an expansion in, say, in this case, in the case of this example, energy over the heavy scale. Now, how exactly do you assign a certain scaling to a certain term in the Lagrangian is what we're going to see in a moment. But first, I would like to say that if we're interested in describing the outcome of an experiment that has a finite precision, in practice, once this ratio, we have a high enough powers of U over M, that this quantity is smaller than the precision of our experiment, it becomes useless to add more terms to your effective action because you are not able to test them. And so in practical applications, effective theories will always contain a finite number of coefficients. Okay? The more precise your experiments get, the more you have to increase the number of terms you include. And the fact that the usual Lagrangians we encounter contain a finite number of terms is because in the vast majority of cases, it is good enough to only keep the first few terms in an effective action. But in general, you should always think of that action as coming with an infinite baggage of terms that you've just decided to drop. Okay, so how exactly do you decide which terms to keep and which terms to drop? This is what power counting is for. And so let me give you a sense of how this works in the particular toy model we're considering. Okay, so we're interested in, we said, roughly relativistic fermions, such that their four momentum components all have roughly, say, the same order. They're of order E. Okay. This is to say that a derivative acting on a fermion field, if I think of this fermion field as being a plane wave, essentially it's going to scale like E as well. And now, by using an uncertainty principle argument, this means that x mu should scale like the inverse of an energy, and that something like a measure of integration that contains 4 x's should scale like 4 inverse powers of the energy. Now, it makes sense to assume that if all the terms in the Lagrangian are to be associated with one particular power of E over m, it makes sense to assume that the kinetic energy, which is what really defines the dynamic of each field, it makes sense to assume that this is a factor of order 1. Okay. And if you do that using these scaling laws above, you find that the kinetic term will scale like 1, provided psi scales like energy to the 3/2. So in this case, psi really scales like the engineering dimension. But as we will see in more complicated effective theories, that is not the case. Okay. So you can use these these arguments to estimate, say that the quartic self-interaction that we wrote before should really scale like E squared over m squared. Higher powers of like a 6-tick self-interaction and so on will scale like higher powers of E over m. Now, of course, having an m in the denominator here already kind of gave away the scaling, but in more complicated effective theories, it's not always going to be obvious how various terms in the action scale. Okay. But it remains the case, even in this example, that when you include a higher and higher order of derivatives or of fields when writing down a term, each of them is going to come with a scale like 1 power of E. And so when you look at the overall scaling of these terms, they're going to come with a scale like higher powers of E over m. Okay, and therefore up to beyond a certain point, they're just going to become negligibly small. In practice, how many of these terms you need to keep in your Lagrangian to match some experimental results depend on how small the ratio of E over m is. And when E becomes of order m, essentially your expansion parameters become of order 1. All the terms in principle should be kept because they become of the same order. And that's where the effective theory stopped being useful, okay? Because, you know, we can get by with the idea that there should be an infinite number of terms only because in practice we need to keep a finite number of terms. But if we had to really keep them all, then it would just, it would be hopeless. So for this reason, in this particular example, the scale M is an example of what is known as strong coupling scale. Okay, at this scale, all your interactions become equally important. This scale is also referred to as cutoff, more colloquially, but for reasons that are going to become more clear in a moment, because when we consider loops, we're not going to regularize them using a cutoff. I find it a bit misleading, so I'm just going to stick with strong coupling scales for these lectures. Very good. And so this is another advantage of going back to one of the questions at the very beginning. Another advantage of thinking in terms of effective theories is that effective theories are able to predict their own demise. Okay? They tell you not just how good, what's the accuracy of your prediction, but they also tell you until what point can you trust your theory and when should you stop trusting it and instead try to come up with a better description that perhaps has different degrees of freedoms, different symmetries, and so on. Okay. In this particular case, it is clear why our effective theory breaks down at this scale. It's because at scales larger than M, we would need to switch to the full theory that now also includes the scalar, because at higher energies, scattering events can also produce the scalars. Okay, so this is sort of how things work. Let's say if you're interested in reproducing tree-level results, but we would like to go beyond that and also reproduce, be able to match loop results. So this is what I'm going to spend on, what I'm going to discuss the last 20 minutes of this lecture. Before I go ahead, do you have any questions about this?
So yeah, there are 3 questions. Mm-hmm. So the first one is again about the j equals 0. Okay. And it's asking, putting j equals 0 from the beginning, don't you end up with an infinite measure?
So very good. Here you're saying. So something I said in passing was that these generating function, as I wrote it, is going to give you the correlation functions that you want, these time order products, only if it is appropriately normalized. Okay. So in practice, that means that to be precise, I should have divided this expression by the integral of the action where all the currents are set to 0. Okay, and if you do that, then essentially, when you integrate over phi and set j to 0, you can integrate over phi at the top and at the bottom, and this normalization problem takes care of itself. Yeah, thank you for asking that.
Okay. So another question is, can the ratio of masses be taken as the expansion parameter?
Yes, absolutely. Yeah. So for instance, not maybe directly field theory example of that, but when you in quantum mechanics, when you treat the hydrogen atom as a problem of a particle in an external potential, you can think of that as having taken the ratio between the mass of the nucleus and the mass of the electron to 0. Okay, so that essentially in the first approximation, the nucleus doesn't recoil or doesn't feel an interaction, feel the interaction with the electron. Okay, that's an example where you have neglected this small ratio of masses.
And we have a last question, which is the following. So why was the effective action expanded in powers of h bar?
Very good. So, so I started with an expansion in power of h bar because in practice, like I said, the matching procedure is carried out by matching, when you can do it perturbatively, is carried out by matching diagrams in the full theory and the effective theory. And usually when we calculate Feynman diagrams in field theories, we calculate them in an expansion in powers of loops, which can also be thought of as an expansion in powers of H bar. And so in practice, as we will see in a moment, when we calculate loop diagrams in the effective theory using only the 3-level effective action, we'll find that we cannot reproduce the results of the full theory at one loop, but we will have to also choose appropriately the one loop part of the effective action. And so this expansion in H bar really matches, if you want, the expansion in loops in the Feynman diagrams.
So there is a quick follow-up to the question about the ratio of masses.
Okay.
And it's been asked, how do you write the higher dimensional operators in this case?
Okay, so maybe next time I can give a concrete example of that. I'll check if in my notes I'm already discussing a concrete example where we have an expansion in powers of masses, and if not, I'll try to give you a quick one next time.
Okay, great. So for the moment, that's all.
Okay, so and just remind me, you said that I had 20 lectures at my disposal, right? No.
Yes, 40 actually.
40, very good, yeah. So we will never cover everything that I wanted to cover.
So
but
you have
okay.
15 more minutes, more or less.
I mean, yeah. So let me start talking about matching at loop level.
Yeah.
And the way you do it, once again, is by comparing loop diagrams in the full theory and in the effective theory. So let's start with the effective theory. And I'm going to work only at lowest order in the expansion in E over M. Okay? In principle, you could do that at any higher order, but just to keep things simple. Okay? So to keep things simple, this is the only diagram you have in the effective theory. Okay, because we have a quartic self-interactions. When you write it down explicitly, it looks like so. Okay. Now, this diagram is clearly UV divergent, and one might be tempted to cut off this UV divergence at the scale K star of order n, just because, you know, we said that this effective theory loses any meaning at energies larger than the mass of the heavy scalar. So why should we even trust, you know, integrating in a loop over fermions that have energies larger than n? Okay. Despite the fact that it would make a lot of sense intuitively, it would actually be a very bad idea to regularize your theory this way, because it would not preserve the power counting rules that I discussed a moment ago. Okay? So in particular, the power counting rule we derived before for the quartic vertex told us that each quartic vertex should scale with some powers of E squared over M squared. Right? If you were to cut off this integral at a scale of order big M, because it's UV divergent, it would scale like big M squared, which means that this M and the one in the denominator would cancel out. And so you wouldn't have this E squared over M squared suppression that you would instead expect expect from the power counting arguments that I gave a moment ago. Okay. Just to remind you, the reason why having definite power counting rules is important is because if you cannot tell how large or small the impact of an operator is going to be, you are not justified in dropping any of them. And since there are an infinite number of terms in the Lagrangian, you will be really in trouble. Okay, so we really want to stick with the definite power counting. And to do that, rather than using an explicit cutoff, which would also have problems, say, in gauge theories, so would also have a variety of other problems, we choose instead to work in dimensional regularizations and in the MS bar scheme, okay, minimal subtraction, modify minimal subtraction scheme. And long story short, when you do that, and you go from 4 to 4 minus epsilon dimensions, you can calculate this loop, and you find that is scale like m cubed over, over m squared. Then there is a 2 over epsilon plus 1 plus log of mu squared over little m squared. Plus, well, that's it. Okay. I'm dropping things that go like epsilon. Okay, so now you see that in dimensional regularization, actually, we have sorry. Okay. So as advertised, we have our suppression of E squared over M squared, as it befits a diagram built out of a quartic vertex. Very good. So this is the loop diagram in the EFT. Now let's check what we can write down in the full theory instead. And let's compare the two things. Now, in the full theory, you have two diagrams that you can write down at one loop. One looks like so, but it turns out that this diagram actually vanishes, and it vanishes for a fairly simple reason, that if you were to cut it, to cut the scalar line, this part of the diagram, which looks like so, would actually renormalize a term in the effective action that is linear in phi, because you see this diagram only has one external scalar line. However, we know that the action is invariant under parity, and under parity phi goes to minus phi. So a linear term would not be invariant. And a linear term cannot be there, and therefore this term should vanish, because otherwise it would generate one. Okay. So this first diagram that we should consider, in principle, in practice, vanishes. And then there is a second diagram, which is just, if you want, the self-energy diagram. Okay. And sorry, I should have said that just for the sake of figuring out how matching works at loop level, I'm just sticking with the 2-point function rather than the 4-point function, because it's just, yeah, it's just simpler to deal with only two external lines. Okay. So when you calculate this diagram, you find that, long story short, that in dimensional regularization, again, it looks like so. P slash plus 2m plus P slash over 2 minus 1/2 plus the log of m squared over mu squared plus little m squared over m squared. Okay, plus little m minus 1 plus. So the final result is not particularly memorable, but there are some points, some comments that I would like to make about the comparison between these two loop diagrams. And so I would like to write it down for completeness. Plus p squared over m squared. Okay. And then there are other terms that I dropped because they correspond to higher order terms in the expansion in powers of inverse scalar mass. Okay. So they're going to be suppressed either by little m over big M or by momenta over big M. Okay. So now, because the first diagram vanishes, this is really the only loop correction we have to consider to the 2-point function of fermions in the full theory. Okay, and obviously, this looks different from what we got in our effective theory. Now, not only looks different, it also looks much more ugly. Okay. So, and this hopefully is going to drive home another advantage of working with an effective theory, which is that when you calculate, say, loop diagrams, they're actually much easier to calculate than if you were to calculate a diagram in the full theory and then just perform a low energy expansion. Now, a few comments about the comparison between these two results. One is that I didn't write down the integral, the analog of this for the full theory. But if I had, you would see, and you can see that from the notes, that these results here correspond, this integral in the EFT is exactly what I would have gotten if I had expanded the integrand in the full theory before carrying out the integral. Okay. So at the pictorial level, you know, this can be viewed as saying that if I take this diagram, and now I rewrite it. I rewrite it like so, and then I contract the scalar line. What I'm left with is precisely the diagram in the EFT. Okay, so expanding the integrand corresponds to like contracting the scalar lines. Okay. On the other hand, despite this connection, the final results that we get at the end, when we, rather than expanding the integrand in the full theory, we carry out the full integral and then expand, the two results are very different. Okay, this tells us that integrating and expanding are two operations that do not commute. And in particular, notice that here we have non-analytic terms around big M equals 0, okay, like the logs, for instance. And here we don't. We only have little m in the logs. And the reason why we miss those is because if we expand in inverse powers of m before integrating, that expansion relies on the assumption of analyticity. And so we have already missed all the possible non-analytic terms in big M. Okay. The divergent terms that go like 1 over epsilon here are also different. And as you know, these terms are what determine, after normalizing, the running of your couplings in your theory. And so this means that the couplings in the EFT and in the full theory also run in a different way. However, one thing that is actually the same in the full theory and in the EFT are the logarithms, the non-analytic piece in the small in the small mass, okay, in the higher scale. And this must be the case, and it's the reason why effective theories are actually able to disentangle scales that are widely separated and sum the large logs that I mentioned at the beginning. This is something we'll see at this point, I think, next in the next lecture. And last but not least, you see that, as I emphasize here, the EFT loop already comes with an expansion in powers of large E of E over M, which means that, and this is true also at higher loops, you get more and more suppression. So this means that if you're interested in performing calculation with a finite precision, not only you need to include a finite number of terms in the action, but also you need to go up to a finite order in the loop expansion. Okay. Now, okay, this is all good. It still remains that these two results clearly are different. And the reason why they differ is because essentially we have only considered the three-level part of the effective action. The difference between these two diagrams can be accounted by adding another three-level diagram that can be obtained directly by the one loop effective action. And so you can prove that if you, okay, I'm not gonna write it down, you have the notes, so if you look in equation 26, you can show that if you add this term to the effective action, you can match exactly the one loop calculations in the effective theory and in the full theory. Okay, and notice that the coefficients in the one loop effective action depend on the renormalization scale mu. So this goes back to the question that someone asked before, whether the EFT was dependent on the scale. And as you can see, these coefficients explicitly depend on the renormalization scale. Okay? So I think this is a good time to stop. I'm gonna continue next time discussing about how to resum large logarithms. But for now, let me stop here.
Okay, thanks a lot, Riccardo. So we have a few questions. So the first one is the following. Can an EFT be applied to calculate some function or observables with relative success? And at the same time, and under the same conditions, could this EFT not work when you calculate another function connected to the first function? For example, can you have a good approximation for a correlation function and not so good approximation for a function built from that correlation function?
I guess the answer is it depends on how this function is built, right? So I try to emphasize that effective theories are a perturbative framework in the sense that observables are always calculated as an expansion, as a series in these expansion parameters. And so as long as, say, the function of the correlation function is, I guess, analytic in the correlation function, and it also admits an expansion in powers of E over M, then you just need to expand this new function up to the order where you can trust your calculation. If that makes sense.
Okay, let's see if there is any reply. So let me ask you the next question in the meanwhile.
Yeah.
So, but it seems like we have a power law divergence, which is 0 in dimensional regularization.
Yes, excellent. Exactly. So this is one of the crucial reasons why we use dimensional regularizations as opposed to say a cutoff regularization. There are many others, as I mentioned, gauge invariance and so on. But this is crucial, and this is also why calculations in an EFT are often simpler, because anytime in an EFT you encounter an integral that does not contain any scale, that integral automatically vanishes. Okay. So dimensional regularization set to 0 all power divergences, and by doing so simplifies your calculations greatly and preserve power counting, as we've seen.
Okay. Then there is another question which I'm not sure I understand. In the linear term, gamma 5 is present to make the term parity conserving.
Yes. I think.
But why the first? Okay, there was a part missing.
Okay.
But why the first loop contribution is 0? So I guess it's the correction with the
this one here.
Yes, I think
yeah,
so.
Very good. Well, it's because right. So this full loop diagram would be a product of two terms. If you were to spell it out explicitly, it would be a propagator for the scalar, and then times this loop correction. And on the other hand, this loop correction here is also something that you would consider if you were interested in seeing how the 1-point function of the scalar gets renormalized, or which is to say, how the coefficient of a term linear in the scalar in the action would get renormalized. Okay. But because phi is odd under parity, it cannot contain terms that depend only on the scalar and are odd in the scalar. Things like phi cubed, phi to the 5th, and also something linear in phi. Okay. And for this reason, this diagram vanishes. Now, you can also see it more mechanically by just writing down the explicit expression and using the properties of traces of the gamma functions, and you see that the trace of the gamma functions just vanishes.
But gamma 5 is there to preserve parity.
That's right, but gamma 5 is something that makes sense. So yeah, parity is preserved, but gamma 5 is something you can use only when in an interaction that also involves fermions, right? Because it's a matrix with spinor indices. So what I'm saying is that a term linear in phi without any psi around in the action is not allowed. But if this diagram I wrote here were non-zero, you will need to have that diagram in your action, and so because it's not allowed, this diagram must be 0. So yeah, I'm happy to talk more about it tomorrow during the Q&A. If
yes,
maybe
if it's still not clear, you can.
Yeah, or feel free also to send me just an email.
Yeah, Sudipta, you can ask it tomorrow and send an email. So let me move on with the questions. So what if right and left parts have different Dirac structures?
So do you mean what if you have a theory that involves left-handed and right-handed spinors with different interactions?
Yes, I guess. So what if the theory is chiral?
What if the theory is chiral? Very good.
I guess, I'm not sure.
Yeah, so then the same exactly the same ideology applies, meaning if you are at energies below the mass of your chiral fermions, you cannot produce them, and therefore you can integrate them out. And in fact, you know, in my notes, I have a section where I actually discuss chiral anomalies and also gauge anomalies in theories where you have chiral fermions. And given the pace today, I would probably cover that in lecture 18 or so. Yeah, hopefully when we get there, you know, we can discuss about that. If not, you know, feel free to email me, or we can talk about it during the Q&A also.
Okay. So this is a more general question. Is there any general theorem to justify the use of EFTs?
So this is a good question. I would say there are many results that gives us confidence in various techniques and tools that we use when we write down an effective theory. There is the one theorem that comes to mind in particular is the Appelquist-Carazzone theorem. It's known as the coupling theorem. That tells us that, loosely speaking, that you know, the effect of UV physics should just be captured by choosing appropriately the values of the coefficients in the EFT. So perhaps maybe that's the best justification for it. But in practice, I think that theorem applies, you know, to, at least was developed, as far as I know, in relativistic, in the context of the relativistic theories of particle physics. Whereas, you know, the modern viewpoint is that effective theories are a framework that you can apply in any context, even when you are at low velocities, and so the relevant space-time symmetries are Galilean invariants. You can apply them when Lorentz invariance is spontaneously broken, and so on. So I don't think there is a general theorem that applies to any case, but in practice, a boatload of experience gives us confidence that this way of looking at nature actually seems to be working.
Okay, so maybe one last question, then the remaining questions we can keep for the Q&A session tomorrow. Would you be talking about running coupling constants?
I will talk a little bit about it next during the next lecture. I won't go into details really, but I will show you why considering the running of the coupling constants is a crucial ingredient in resumming these large logarithms that I mentioned a few times today. So one ingredient is matching that we talked about today, and the next one is going to be running. And so we'll see that tomorrow. Okay,
great. So I think this is a good moment to stop. So Riccardo, thanks a lot for the very nice set of questions. And I would like once again to thank everybody for the attendance. So we reconvene tomorrow morning at 9 a.m. Brazilian time. Again, we're going to have the first lecture of the standard model by Andrea Romanino, and then we move on with the same schedule as today. So thank you, everybody. See you tomorrow.